Good evening, Lamai. Okay, let's start the session for today. Right. Last day we had discussed about the Lewis structures, right? Lewis structures and how we Lewis structures and how we are to draw the structures, right? With the starting session of the unit 2, right? So today let's discuss about the resonance structures. So our major topic here today is to discuss about the resonance. So when it comes to resonance, resonance structures, resonance hybrid, and how to use the resonance hybrid to come up with the bond lengths and bond strengths, those will be discussed, right? Okay, today our lesson is about the resonance structures, right? So first of all, let's draw some structures for the N2O molecule, the molecule N2O, and then quickly come up with the idea what this resonance means and what are these resonance structures, right? What this means, right? Okay, first with the knowledge of the last day we have gained, let's draw some structures for the N2O molecule. So I'll quickly go through the steps we had followed last day, right? Then let's come up with the N2O, right? So I'm going to draw the N2O molecule, right? Again, last day with the homework, I think question number 6 there in your tute, right? It was about N2O, the drawing Lewis structure of N2O, right? So let's do the working there and let's come up with the N2O Lewis structure, and then we can come up with a clear idea what this resonance means, right? Okay, so let's draw this stuff, right? So when it comes to N2O, let's do the electron count first, right? So with the electron count, right, we can come up like this, right? So with nitrogen, right, right, some 5 electrons will be given by one nitrogen, right? 5 into 2, right, as 2 nitrogens are appearing. So nitrogen is in your group 15, that is why 5 electrons are given to the valence electron count, and 2 of nitrogens are there. So with oxygens, right, oxygen as group 16 element, 6A element, one oxygen will give 6 electrons to the valence electron count. So all together you will have 10 electrons there, right? 10 electrons there. So if you are to come up with the electron pairs, number of electron pairs, so 10 have to be divided by 2, that will give you 5 electron pairs, 5 pairs. So if you are to think of the N2O, the skeleton, N2O, the skeleton, right? Let's draw the skeleton here, N2O, the skeleton, right? So for the skeleton of N2O, right, 2 electron pairs are used for the skeleton, right? 2 used, right? Okay, that is with the skeleton, right? The N2O. So the remaining pairs, which are known as lone pairs, the lone pair count is going to be then 3, no? So N2O, right? So 10, sorry, it is 16, sorry for that, it is 16. So 8 pairs for the skeleton 2 is used. So lone pair count is going to be 6 pairs, right? So let's give those 6 electronic pairs to your skeleton, right? Let's give you those 6 electronic pairs to your skeleton, right? Okay, this is your skeleton, right? So when allocating electrons, when giving electron pairs to the skeleton, first you have to fulfill the octets of the cone atoms, right? So fulfilling octet means completing 4 pair situation with those second row non-metals, right? So 1 electronic pair is there with the oxygen, completing the 4 pairs means another 3 electronic pairs should be given. The octet is completed with this oxygen. So we have to complete the octet of all the cone atoms normally, right? So 6 electron pairs have been allocated now, right? Okay, so now we have a problem. What is the problem? The problem is with the center atom. after allocating the electron, we have to look at about the center atom. If it is a second row non-metal, definitely it should fulfill the octet. If it is a second row non-metals, our major concern is to fulfill the octet. If it was a third row above atom, then our major concern is to come up with the least charges on that atom. Anyway, this is second row non-metal, so we have to fulfill its octet. So actually, when we are trying to fulfill this guy's octet, we have three methods. The three methods are available. Three such methods are available to complete the octet for this nitrogen. The one method is by giving both the electronic pairs, the 4-pair situation should be completed with this nitrogen. So 2 pairs are already going around the nitrogen. So this nitrogen needs another 2 pairs. So both the pairs can be given by this nitrogen. That is one method of fulfilling the octet for the center nitrogen. So if so, we will come up with, right, a structure like this. If that is the electron movement to complete the octet of this nitrogen, you will come up with a structure like this, right. So your structures, sorry, I will draw it in red color, right. So for the red color movement, right, electronic movement, so your structure would looks like this, right. Okay. If you are doing the red colored electronic movement to complete the octet of this center nitrogen. So if you allocate the charges on these atoms, so 1, 2, 3, 4, 5 electrons are going around nitrogen. This should have 5. You have 5 electrons are going around, so no charge. So this nitrogen should have 5 electrons, but now the number of electrons going around that nitrogen is 1, 2, 3, 4. 5 should be there. Only 4 are going there. So 5 minus 4 is plus 1. So with this oxygen, there should be 6 electrons to go around the oxygen for a neutral oxygen, but now you have allocated 1, 2, 3, 4, 5, 6, 7. 6 should be there. Now you have allocated 7. That means minus 1 is a charge of that oxygen. So this is the structure you will get if you fulfill this nitrogen's octet like this. So one can fulfill this guy's octet by donating only one pair from this nitrogen, and from the other pair can be donated by this oxygen, right. There is another way of fulfilling the octet of this nitrogen. So if you have done like that, so you will come up with a structure like this. So already one pair was there and another pair was given in between 2 nitrogens, right. So already one pair has been there and another pair was given by the oxygen. So 2 bonds are there between the nitrogen and oxygen. So 2 pairs are remaining like this. For this one also 2 pairs are remaining. Then let's put the charges on these atoms, right. So if you put the charges on this atom, 1, 2, 3, 4, 5, 6, 5 should be there, 6 are going there. So 1 electron is in excess, so minus charge. There should be 5, but 1, 2, 3, 4, only 4 are allocated. So the charge is plus 1, lack of an electron. There should be 6 here around the oxygen. Now you are with 1, 2, 3, 4, 5, 6. 6 here and 6 are there. So the oxygen carrying no charge there, right. So and one can think of, right, kind of electron donation, right, like this to fulfill the octet. Both the electron pairs to be donated by the oxygens. Another method of fulfilling the octet, the third method. If you are to do so, right, you will come up with a structure like this. These are 3 available methods to complete the octet of the central nitrogen. So if you have to allocate the charges would look like this, right. Charges would look like this 2 minus here, right, 2 minus here, because nitrogen should have 5 electrons for a neutral nitrogen, but now you have 1, 2, 3, 4, 5, 6, 7. You have allocated 7 electrons. 5 minus 7 is minus 2. That is how the minus 2 charge obtained by the nitrogen. So these are 3 acceptable Lewis structures. One can draw for the same N2O molecule, for the same N2O or the same skeleton. Now we have already written 3 acceptable Lewis structures. Actually these things, if you can draw more than one acceptable Lewis structure for a given skeleton, then we refer them as resonance structures. Resonance structures. So that is the definition. What are resonance structures? Resonance structures are the Lewis structures if we are able to draw more than one acceptable Lewis structure for a given given skeleton, right? For a given skeleton, for a given atomic skeleton, for given molecule, if you can draw more than one acceptable Lewis structures, then those are referred to as resonance structures. So these are considered as resonance structures, right? These are the resonance structures. Resonance structures. Normally we denote these resonance structures with this symbol, this double headed arrows. With this symbol, normally we denote the resonance structures, right? So if this kind of a thing was appearing, A and B with this symbol, this says A and B are resonance structures. A and B are resonance structures. That means A and B carry the same atomic skeleton. A and B carry the same atomic skeleton. A and B are with the same net charge. The net charge of these molecules are equal to the charge here, the 0. So A and B, if you look at a situation like this, so A and B are resonance structures because of this sign. That means these guys are with the same atomic skeleton. These guys are with the same net charge, right? So that idea should be known with this symbol. This is the symbol which indicates that the constituent species are resonance structures related by the resonance, right? Okay, these are the resonance structures. So you got the clear idea what this resonance means, right? These are the resonance structures one can draw for the N2O molecule, right? Okay, so you got the idea now. That is about the resonance structures, right? Right. Our first consideration is done. Resonance structures, right? Okay, now let's discuss about how to comment on stabilities of these resonance structures. That is our second consideration for today. Now we had some, we are with good idea what this resonance means, what these resonance structures are, right? Now let's concern about how to comment on the stabilities of these resonance structures, right? So we are with three acceptable Lewis structures which can be drawn for the same N2O molecule, right? So let's discuss about commenting on the stability of these ones, right? Okay, now next consideration is commenting on the stability, right? So stability comments, it's done. Second thing is about, right, comment on stability. That is what now we are doing, commenting on the stability, right? Okay, stability concerns, right? Okay, so how to comment on stability, right? So there are structures, there are acceptable Lewis structures which are concerned as stable structures as well as unstable structures, and some are concerned as less stable structures. So we should be able to correctly label whether these structures are stable, unstable or less stable. Those are the three labels we use in A levels, right, to comment on their stabilities: stable, less stable and unstable. Let's discuss about the stability rules. What are the rules we can apply, right, to concern about the stabilities of these structures, right? Okay, few rules are there. Before that, let's consider about what this stable means. Before going for those rules, right, stability rules, let's discuss a bit about what this term stable means. Stable, yes. So stable means like this. It's kind of a thing like this. Stable means if you are not changing if something is not changing for a longer period of time. If something is not changing for a longer period of time, right? If something is stand for a longer period of time without a change, then we can say such a thing is stable. Such a thing is stable, right? So stability is that if you are not changing for a longer period of time, right, you are stable. So sometimes we say that guy is very stable, his words are very stable, right? He is saying again and again the same thing. He is not changing throughout the years. He is saying the same thing. He is stable. His words are stable, like that. So if something is not changing for a long period of time, we can consider it as stable. If something is changing, if something is to change in no time, with a quick time interval, if something changes their conformation, if some bonds are to be broken, if some electrons are to be transferred with the atoms, the structure changes with no time, then we consider such structures as unstable or less stable, right? Okay, that is the meaning of stability, right? So actually, for not changing for a longer period of time, not to change for a longer period of time, basically your interactions should be less. Your interaction should be less. If you are interacting heavily, with the other particles and the stuff, then you will change eventually, right? As we are interacting with the others, right? So we are changing, our ideas are changing. As we are talking with the others, their ideas are also coming towards us, towards our brain, and so we are trying to think of those ideas as well, so we will change them. If you are not talking with others, if you are not interacting with others, then we won't change, right? So to become stable, to be as stable, not changing for a longer period of time, it is better to have less interactions. More the interactions with you, that means your stability decreases. That is the idea, no? Right. Okay, so what will happen? So the case is this. So if you are with charges, that is what happens, right? Let's say you have a structure like this, right? And the structure is with charges. Some positive charges, right? Structure is with charges. Okay, then what will happen? If your structure is with charges, right, towards that structure, the negative charges will attract. If you are with a plus charge in your structure, the negative charges is attracted, right? If you are without charges, no particles will attract towards you. If you are with charges, the opposite charge particles will attract towards you. They will interact with you. That is why we are saying a structure with charges are with less stability. If you can draw a structure without any charge, on atoms, then that would be the best structure. Because no interactions will occur with the outsides. So that you can stay for a longer period of time without a change, because with no as you are not dealing with any interactions, right? When you are with charges, your structure becomes unstable. So basically, right, bearing a +1 charge, -1 charge is okay actually. Bearing a +1 charge, -1 charge is okay. But if you are with +2 charge, +3 charge, what will happen? +2 charge, +3 charge means, right, not the particles which are nearby, but also the particles far away from you. The opposite charge particles far away from you also feel the charge of you, so that even those particles will attract towards you. So bearing a heavy charge, more than 1 unit of charge, will decrease your stability heavily. So bearing a +1 charge, -1 charge is okay. For some molecules, we can't draw any structure without charges, lamai. So this molecule even we can't draw any structure, any acceptable structure fulfilling the octets, we can't draw any acceptable structure without charges, right? So for those instances, bearing +1 -1 charge is okay, but if you are bearing some greater charge, greater magnitude of charge, that means more than 1 unit of charge, +2, +3, -2, -3, if you are bearing that kind of a larger magnitude of charge, then this is what happens. Not only the particles which are close to you, but also the particles which are far away from you also attract towards you, right? So that your interaction amount will become very large, so that your stability will be very less then. So the structure becomes less stable when you are carrying a charge with more than 1 unit. Those are the ideas, right? So that is how the structures become unstable, less stable, right? Okay, those are the main reasons, right? Okay, so let's again discuss one by one, point by point, clearly how to comment on the stability. Now I think you have got some clear idea about what stability means. Let's discuss one by one the points what we should concern to comment on these stabilities of these structures, right? Okay, so these are the points, right? Let's come up with the points now, right? As you know the reasons now, no? Right? These are the major points. So you have to follow the points one by one. Right? To check the stability of the structure. The first concern, right? The first concern is, if you can draw a structure without charges on any one of the atoms, if you can draw a structure without charges on any one of the atoms, that structure is the most stable structure you can draw. Because no interactions with the others. So you can stand for a longer period of time without a change, right? Okay, but here you clearly see such a structure is not there. So we can't say, right? We can't comment by looking at that point whether the structures are stable or not, because all the structures are carrying some charges. So that point we can't think of for these three resonance structures, right? The first point is what? If you can draw a structure without charges on any of atoms, then that is the most stable structure. The best acceptable structure. For this example, such a structure is not there, right? So we are not going to concern about that thing, right? So this point is not valid with the resonance structures of N2O. Then we have to consider the next points, other reasonings. The reason number 1. The first two reasons are about some these reasons are about taking your structure into a unstable nature, right? The reasons. First reason, if a positive charge appears on most electronegative atom of the system, then the structure is considered as a unstable structure. So if this thing is there, so we consider that structure as an unstable one, right? Why is that? Always ask why is that. The reason is, electronegative atoms are the ones which are more keen of electrons. So bearing a positive charge on that means that guy is lack of electrons. That guy is lack of electrons. That can't be for a long, no, Lamai. That can't be for a long, no. That can't be for a long, right? Because that is the one most keen of electrons, right? So that then what will happen? That guy will grab some electrons from one of the atoms, from the nearby atoms. That most electronic atom will grab some electrons towards itself, so that the structure will change eventually. With no time, the structure will change. That is why we say you can't have a stable structure with a positive charge on most electronic atom, because that guy will grab some electrons from the nearby atoms and the structure will change. So those structures are highly unstable, eventually quickly change. That is what means by unstable, right? So we have such structures here. See, this one is unstable, this one is unstable. See, the most electronic atom of this compound is oxygen. Nitrogen is with 3.0 electronity, oxygen is with 3.5, the most electronity is oxygen, but it is bearing a positive charge. So that is unstable. So this structure is unstable. So you can comment this structure as unstable. The other structures are not with such a problem. This is unstable. What is the reason? You can write the reason. Reason is positive charge on most electronegative oxygen atom. That is the reason. That is the reason to become unstable. We have another reason. Two reasons are there for structure to consider as unstable, right? The second reason is adjacently connected atoms are with same signed charges. That is the second reason. Structure to become unstable. That is another reason. What is happening when this thing happens? When adjacently connected atoms are with same sign charges, the repulsions will occur. The repulsions will occur. If the two atoms are with same sign charges, what will happen? The repulsions will occur. Ultimately, it will break the bond. It will change the structure. Unstable. Structure will change in no time. Unstable. Right? So even with the negative charges, if the adjacent connected atoms are with same sign charges, repulsions will occur and bonds will break. Structure become unstable. So that thing happens with this structure. These two atoms are adjacently connected atoms with same sign charges. So this is unstable due to that also. Two reasons for this structure to become unstable, right? So we can write the second reason: adjacently connected atoms are with similar signed charges. Those are the reasons for a structure to become unstable, right? No, structure to become unstable. Okay, so these guys are not coming with those reasons. So these are not unstable structures. Okay, so stability reasons should be considered in order, right? In order. First we consider these two things, right? If these 2 points are not appearing with your structures, then those are not unstable. These two are not unstable. We can't combine these two as unstable. Then we are coming up with the third point. So third point is about less stable. That is about less stable. So if you are with the third point, such a structure is referred to as less stable, right? These are less stable point. So these two things should be considered orderly, right? In order. Third point is, if you are with a more than 1 unit of charge, on a considering atom, that is referred to as high charge density on considering atom, on, let's say, atom X, any kind of atom. So high charge density, this comment will be written when you are with a more than 1 unit of charge, that means -2, -3, +2, +3 kind of charge on atom. So here also we can see that more than 1 unit of charge, but we can't comment this as less stable because we are coming with the order. This structure is considered as unstable. Right? So we can't comment it as less stable. It is unstable already, right? Okay. We have to consider the points in order, right? The fourth point is about high charge dispersion. That is the fourth comment. High charge dispersion or high charge distribution. So this comment is written when you have atoms, you have more atoms with charges compared to the more stable structure. This comment can be written only when you have more atoms with charges compared to the more stable structure. First of all, there should be a more stable structure, right? Compared to that, if you are with more atoms with charges, then only you can write this comment. This is a comment for consider the structure as a less stable one. And keep it in mind to comment on this. Before that, you should identify the most stable structure. Right? Relative to that, if you are with more atoms with charges, then only you can come up with this comment. Right? Okay. There is another comment, right? Which leads for your structure to become less stable, right? Okay. So for these two atoms, for these two structures, those 2 points are not valid. Not valid, because out of these two, one of the thing should be the more stable structure. So compared to that, the other one is not carrying more charges, more atoms with charges. So that fourth point is not valid for these two as well. These are the only 3 resonance structures possible, right? Okay. Fifth point. So actually, Lamai, if these 4 points are not there with your structure, if the concerned discussed 4 points are not there with your structure, then we comment those structures as stable. If the 2 reasons to become unstable is not there, if the 2 reasons to become less stable is not there, then your structure is stable. If it is not unstable, if it is not less stable, then it is stable. No? It is stable. No? So these 2 structures are considered as stable. So you have to concern these comments in order, right? Right. So these 2 structures are considered as stable, right? Okay. Then few more stuff for structure to become more stable. Few more stuff to consider for structure to become more stable than the other. So to consider which is the best structure, which is the most stable structure, we can concern about few more reasons, right? The 5th and 6th points. Actually, those points are appearing with these structures, right? What are those points? 1 point, right? If your structure is with a negative charge, on the most electronegative oxygen atom, or with the most electronegative atom, most probably it is the oxygen. Nah? If your structure is with a negative charge on the most electronegative atom, then such a structure is considered as a stable structure, and it will attain a greater stability by that point, right. So here such a structure is there, see. So we can say this guy is more stable as you are with a negative charge on more serotonin oxygen, more serotonin atom oxygen, right. So that is one reason for become more stable. The other reason to become more stable is adjacently connected atoms are with opposite sign charges. The two reasons are the opposite of these two. Right? Adjacently connected atoms bearing opposite sign charges. Then what will happen? These two will attract heavily. That will confirm this bond. Confirm this bond means bond is not going to break. That means this structure can exist for a longer period of time without a change because the bonds are not breaking. Right? So bonds will strengthening by the attractions of these two atoms as those are bearing opposite sign charges. So that is a good reason to become more stable, right? So adjacently connected atoms are with opposite charges. Adjacently connected atoms are with opposite charges, right? So even this structure carrying that point, right? These two guys are with opposite charges. Are with opposite charges, right? So that is how we are supposed to comment on the stability, right? So we can draw three resonance structures for the N2O. Right? Those resonances are indicated by this sign, right? And they are with non-equal stabilities. The stabilities differ. This one is unstable, this is stable, and this is the most stable structure, and we have discussed the reasons to consider them as stable, unstable, and less stable, right? So that is the first discussion for today, right? So resonance structures are the ones, resonance structures are actually the structures we can draw, the acceptable Lewis structures we can draw for the same skeleton, right? If you can draw more than one acceptable Lewis structure for the same skeleton, those are referred to as resonance structures, right? So those could be with unequal stabilities, right? So this is a good example for that, resonance structures, right? So we'll draw a few more resonance structures now, right? And let's try to comment on their stabilities as well, right? Let's draw a few more, right? So with your next example also, SCN minus, another good example. Let's draw some resonance structures for SCN minus as well, right? SCN minus as well, right? Let's quickly draw for the SCN minus as well the resonance structures possible, right? The SCN minus. Quickly come up with the electron count as well, right? Your central atom is carbon. Central atom is carbon. It is the least electron atom, right? 2.5. Sulfur is 2.6, right? The carbon is the central atom, right? So the carbon, right? So first do the electron count and SCN minus, right? SCN minus, central atom carbon. First do the electron count, right? Sulfur carrying 6 electrons, sharing 6 electrons to valence count. Carbon sharing 4 electrons, group 14. Nitrogen sharing 5 electrons. So altogether you are with one more electron in excess, minus 1 charge. So altogether you are with 12, 16 electrons. So electron pairs 16 divided by 2, that is 8 pairs. Then how many allocated for the skeleton? For the skeleton, 2 pairs are allocated. So you are remaining with how many pairs? 6 pairs. Right? So allocating those pairs to these cone atoms. First to the most solitary atom, completing the octet of that thing, means completing the 4 pair situation for that. Then you can complete the octet for the other cone atom. 6 are gone. Now this carbon is not fulfilling the octet. We have problem. So we have to donate 2 electronic pairs towards this carbon. 2 electronic pairs towards this carbon. Right? Because 4 pairs should be there around the carbon as it is a second non-metal. Right? So those 2 pairs can be donated both by this sulfur, then you will come up with this structure, right, this structure. So you can mark the charges 1, 2, 3, 4, 5, 6 should be the only 5 is there, so plus 1 charge, right. So 1, 2, 3, 7, 1, 2, 3, 4, 5, only 5 should be there for nitrogen, so minus 2 charge. Carbon is without a charge, 4 should be there and 4 is there. Or one can donate the pair, both the pair from the nitrogen, so that you will come up with this kind of a structure. Between carbon and nitrogen, 3 shared pairs are there with the donation of 2 pairs towards the center. So this is the structure. With this structure, if you allocate the right charges, this will come up with a minus charge, because only 6 electrons should be around sulfur, as it is group 16 oxygen's group, but now we have allocated 1, 2, 3, 4, 5, 6, 7. That is a Cn minus, another resonance structure, and one can donate 1 pair each from sulfur and nitrogen towards the center, so that you will come up with this kind of structure. No? So when you have to allocate charges, you will have a minus charge here, that the charges are without charge. So these are the 3 resonance structures possible for the Cn minus. 3 different structures, 3 different acceptable Lewis structures which can be drawn for the given skeleton, for the given molecule or the given ion, the resonance structures. Right? These are the resonance structures possible for Cn minus. So let's comment on their abilities. Right? Okay. So first reasoning. What are the first reasons? Reasons to become unstable. What are those? Positive charge on the most solitary atom. Adjacently connected atoms are with same sign charges. Do we see any one of those things appearing with these? Positive charge on the most solitary atom? No, the most solitary atom of this system is nitrogen. Nitrogen is not bearing any positive charges with any of the structures. So that point is gone, not there. The second point, adjacently connected atoms are with same sign charges. No, it is also not there. So neither of these structures are unstable. No worries with that. Right. Second considerations, the third and fourth points. Those are considerations about less stable situation. Right. High charge dispersion and high charge density. First, let's consider about the high charge density situation. If one of your atom carrying more than 1 unit of charge, then that is referred to as a high charge density situation. -2, -3, +2, +3 situations. Yes, we see such a charge appearing here, this nitrogen. So this is a situation with high charge density. So this structure is less stable, less stable, less stable. What is the reason? High charge density on nitrogen. High charge density on nitrogen. If you are with more than 1 unit of charge on one of your atoms, that is high charge density situation. That is a reason to become less stable. This is less stable. What is the other reason? What is the other reason to become less stable? High charge dispersion. High charge dispersion. Yes, that is also appearing with this structure. High charge dispersion. What is that? High charge dispersion means when you have more atoms with charges, when you have more atoms with charges compared to the most stable structure you can draw, compared to the most stable structure you can draw, if you are with more atoms with charges, then those are referred to as high charge dispersion situation. So here we see that one of these things should be the most stable structure, no? One of these two things should be the most stable structure, right? So that this structure is with two atoms with charges. Compared to these things, it is a high value. Compared to these structures, only one atom with charges, two atoms with charges is a higher number. So more atoms are with charges compared to the most stable structure. One of these should be the most stable. So it is a reason to become unstable, less stable. So another reason for to become less stable is more atoms with charges. This is written as high charge dispersion or high charge distribution, right? More atoms with charges. High charge dispersion or distribution. Right? So that structure is less stable. Less concerned about these two. The next reason. So reasons to become less stable is also not applicable with these two structures. High charge dispersion situation, no. High charge density situation, those two situations are not there with these two structures. Let's consider the next reason. So these guys are, first of all, we can refer these guys as stable, first of all, right? Because if the reasons to become unstable or stable not appearing, then those structures are stable, na? Those structures are stable. Reasons to become unstable or less stable not appearing with these two structures, those are stable. So now we are going to discuss, now we are going to select which is the most stable, If you have more reasons to become more stable, then that will be the most stable structure, right? Okay. So to become more stable, what are the reasons available? Yes, one thing is adjacently connected atoms are with opposite sign charges, but here such thing is not appearing. The second reasoning is, right, most electronegative atom of the system bearing a negative charge. So here with this system, what is the most electronegative atom? That is the nitrogen. Nitrogen with its 3.0, this is 2.5 and this is 2.6, right? Nitrogen is the most electronegative atom, that guy bearing a negative charge. That means that is a reason to become more stable, right? This is the more stable. The reason is what? Most electronegative. Atom. Nitrogen in the system is nitrogen. In the system, this nitrogen bearing a negative charge or negative charge on the most electronegative atom of the system. Negative charge on the most electronegative atom of the system, right? So that is the most stable structure. So that is how we are supposed to comment on these structures, right? Okay, right. That is all about resonance structures, right? That is all about drawing the resonance structures, right? And commenting on their stabilities. Actually, here we have discussed about two. I have discussed about two examples. With both the examples, I have concerned some asymmetric skeletons. Some asymmetric skeletons have been discussed, right? So we'll discuss a symmetric skeleton as well. We'll discuss a symmetric skeleton as well. That is better to consider such a skeleton as well to when going towards the next topic, which is actually known as the resonance hybrid. Okay, right. So these are some resonance structures. Okay, so let's go. If you are to look at your note, right, in your note, right, so at the page number, which one? At the page number 9, at the page number 9, these structures are there, resonance structures, that note is there. You can go to that. The resonance structures note is there at the page number 9, right? And at the page number 6, no, at the page number 6, those stability concerns, the reasons are there. So go to that as well. Those are the things we have discussed now. Right, just completed, right? So stability reasons are there at the page number 6. You can draw these things at the page number 6. Even this one, even the earlier case, right, with the N2O. So that resonance structures note is there at the page number 9. Just go to that and do the homework as well. So few molecules are there to draw the resonance structures, right? So few molecules are given. So if you need, I will draw few one or two again, another one. Right, I can draw another resonance structure for you before going to resonance hybrid. Right? Do your homework, Lama. Do your homework at home. Right? So at the page number 9, few molecules are there for you to draw the resonance structures. Right? Okay, do that. I'll do one of those again, right, for you to come up with good knowledge, right? So I'll draw the resonance structures for HCO3 minus, right? Okay, let's draw for HCO3 minus as well, right? HCO3 minus, which is appearing in the page number 9, right? This is completed, so you can take a screen capture if you need. The 9 people, right? Yes, online girls, do you have any questions? If you have any questions, just use the chat box, or you can ask by the mic as well, right? Or you can raise your hands, right, so that I can hear, right? Okay. Let's quickly do the next stuff. I'll draw another one of those, right, to quickly gain some more knowledge, right? So let's draw the resonance structures for carbonate before going for the resonance hybrid things, right? Let's draw the resonance structures for carbonate. So HCO3 minus. HCO3 minus. HCO3 minus. So it is an asymmetric molecule. Another asymmetric one, no? Yeah. HCO3 minus. So HCO3 minus. First do the electron count. With the hydrogen you get 1 electron. With the carbon you get 4 electrons as group 14. With 3 oxygens, 1 oxygen gives 6 electrons each into 3, as 3 oxygens are there, and minus 1 charge is there, so another electron is added. That is what minus 1 is says, right? You have one more electron than the electrons in Hc and 3 O's, right? So the summation is 18, 19, 20 and 24. 24 altogether electrons. So electron pairs 24 divided by 2 is 12 pairs. Then for the skeleton, the HCO3 minus skeleton, right? HCO3 minus skeleton. Skeleton is this. Skeleton is this. So for that skeleton, 1, 2, 3, 4. 4 pairs have been used. So the remaining is 8 pairs. Remaining is 8 pairs, which are known as lone pairs to allocate. Eight pairs. Okay. Let's assign these 8 pairs. Right? 8 pairs. First allocate the pairs to the cone atoms, fulfilling the octets. Octet means 4 pair situation should be fulfilled. So 1 pair is there, 2, 3, 4. 4 pairs completed for this oxygen. 1 is there with the oxygen. 2, 3, 4. 4 pairs are completed with this oxygen as well. So when then comes to this hydrogen. So hydrogen is not supposed to fulfill the octet. Hydrogen is group first row element. So only 2 electrons are allowed with the hydrogen's valence shell. That is completed now with the bond. 2 electrons are there. So hydrogen is not concerned to give the electrons. So next atom. Ultimately we come to the center, right? If this is not there, then for this one we need we have another 2 electron pairs left, right? We have with 2 electron pairs, so we can give those to this atom, right? So that is that guy's octet is also fulfilled as 4 electron pairs are going around that oxygen. 1, 2, 3, 4. 4 electron pairs means octet, 8 electrons, right? Okay. After allocating the 8 electronic pairs, now we have to concern about this center atom. Yes, it's a second row non-metal. So octet should be fulfilled with that atom as well. So 4 pairs should be fulfilled with this carbon as well. So only 3 pairs are going around still. So 4th pair can be donated by this oxygen. 4th pair can be donated by that oxygen. So if you are to do so, right, you will come up with this structure. You will come up with this structure. Right. So if you have to put the charges, this will carry some minus charge. Right. So one can donate the 4th electronic pair towards the carbon like this, so that you will come up with this structure. Right, this structure. Then you can allocate the charges on these atoms, right? So for oxygens you should have 6 electrons, but this oxygen this oxygen is with 1, 2, 3, 4, 5, 6, 7. 6 should be there and 7 is there. So 6 minus 7 is minus 1. And these are carrying 6 electrons each with this oxygen, so no charges there. 6 should be there and 6 are allocated. Carbon is also without a charge, right? So these are 2 resonance structures. These are the 2 resonance structures we can draw for the HCO3 minus, and these are referred to as resonance structures with equal stability. These are referred to as resonance structures with equal stability, right? These are referred to as resonance structures with equal stability. Both are stable. Both are stable, right? Both are stable. So one can see these are resonance structures. Resonance structures with equal stability. Resonance structures with equal stability, right? So both are considered as stable structures. Negative charge is on the most oxygen as well. no reasons to become unstable or stable. Yeah. So such resonance structures can be drawn for HCO3 minus, right? So such kind of situations are also there, right? Sometimes the resonance structures may have equal stability, because such things will appear when with the symmetric skeletons. With the symmetric skeletons, such things will appear, right? This skeleton is symmetric, you know, yeah, kind of symmetric skeleton. So that is what we expect, right? So that is all about the resonance structures, right? Resonance structures and their stability reasons, right? Okay, we have a question. Right. Okay. Now it's done. Right. So that is how we are supposed to draw the resonance structures. So do your homework, right? And send to the class number line, so you can correct them. If you are doing your homework and send to us, right, we will correct it and comment you, right, about your mistakes, right? So do your homework and send to us, right? Our number is there with you, right? So then we can correct them if you have some wrong answers are there. Okay, so let's go to the next session. The next session is about resonance hybrid, the concept of resonance hybrid. Let's discuss about that thing. Resonance structures are okay now, those are clear now, right? Okay, let's come up with the resonance hybrid. So we quickly discuss about the topics for today. Then if you are left with some more time, then we can draw few more resonance structures. We can do more exercises, right? So if not, you can do those at home now, right? Okay, so let's discuss about the next part for today. This is referred to as the resonance hybrid. Resonance hybrid, the concept of resonance hybrid. Resonance hybrid. Resonance hybrid. Right. Okay. Let's discuss about this thing. What this means and what is the importance of this thing. What is the importance of a resonance hybrid? Okay, importance of resonance hybrid. Right. The idea is this. Right. Okay. Let's discuss the importance of a resonance hybrid and what this means, right? To have an idea to answer those questions, first let's go through the resonance structures of carbonate. Let's draw the resonance structures of carbonate, and then after that we can answer those questions. Why we need a resonance hybrid? What is the importance of that resonance hybrid, considering resonance hybrid, and what is that? All the questions can be answered after drawing the resonance structures of carbonate. Let's draw the structures, right, and see, right, what this means, right? Okay, I'll quickly draw the resonance structures of carbonate, right? So for the carbonate molecule, right, first of all, by electron allocation, you can come up with like this. You can come up with a structure like this, right? After electron count and the stuff, right, you will come up with a structure like this for the carbonate, right? For the carbonate, you will come up with a structure like this, right? After that carbon and the count sign and the stuff, right? So after the electron allocation, there are three methods. There are three methods to fulfill the octet of this carbon. There are three methods to fulfill the octet of this center carbon. There are three methods to fulfill the octet of the center carbon, right? So the three methods are, right, one can allocate the electron pair from here, right? So it will give you the structure, it will give you the structure, right? We are two minus charges on these two atoms, right? Or one can allocate lone pair from here to complete the octet of this carbon, right? That will give you this resonance structure, or one can allocate one of the lone pairs from here to here to give the octet of this carbon. So that this structure will form. This structure will form. So these are referred to as resonance structures or resonance structures with equal stabilities. All the three structures are stable structures. All the three structures are stable structures. No reason to become unstable. All the structures are stable structures. For the carbonate. So then we have problem. What is the problem? The problem is when we have this kind of more than one stable Lewis structure. If we can draw more than one stable Lewis structure for a given compound or given species, for a given ion or a compound or a species, if you can draw more than one, stable resonance structure for a given species, then a big problem arises. What is the problem? The problem is actually which structure represents the actually existing species in the environment, right? We have three structures. I label them as structure A, structure B, and the structure C. So actually, which structure represents the actually existing CO3 2 minus, actually existing carbonate ion in the environment? Which structure correctly explain that thing? With that carbonate ion, actually existing carbonate ion in the environment, do we have a double bond at the left hand side? Do we have a double bond with the left hand oxygen or a single bond with the left hand oxygen? With the naturally existing structure of carbonate, do we have a double bond with the left hand oxygen or a single bond with the left hand oxygen? Do we have a double bond with the right oxygen? So the single bond with the right oxygen, or a double bond or a single bond? Do we have a single or a double bond with the oxygen at the bottom with the naturally existing structure? So actually this one or this one or this one, which represents the actually existing molecule in the nature. So that is the big problem arises when you can draw more than one stable Lewis structure for a given species, which represents the actually existing species in the nature. Actually, truly speaking, none of these representing the actually existing carbonate ion. That is the idea. None of these representing the actually existing carbonate ion in nature. Then what is the diagram, what is the form, what is diagram of the actual existing carbonate looks like? How the actual existing carbonate looks like if none of these are true for the actual existing carbonate. So that will be represented by the resonance hybrid. The actually existing carbonate is a hybrid. It's a hybrid of all these stable resonance structures. The actually existing carbonate is a hybrid of all the stable resonance structures. With this structure you have a double bond here, but here and here no double bonds. So actually existing structure is a hybrid. That means in actual existing structure you don't have a double bond, you don't have a single bond at this space, but you have a bond in between the double and the single, the hybrid, right? So in actual existing structure that will be the form. Actually that will be represented by the resonance hybrid. So I think you got some idea about what a resonance hybrid means and why we need that. What is the importance of drawing a resonance hybrid, right? When you have more than one stable Lewis structure for a considering species, then the actually existing structure is represented by none of those but by a resonance hybrid. The resonance hybrid of all the stable resonance structures, right? Okay, the idea is clear, right? Then let's discuss how to do the resonance hybrid. Let's discuss how to draw the resonance hybrid, right? By concerning all of these stable Lewis structures or stable resonance structures, right? Let's start with the carbonates resonance hybrid. Let's start with the carbonates resonance hybrid. So I'll come up with the carbonates resonance hybrid to give you the clear idea about how a resonance hybrid to be drawn, right? Okay, let's try to draw the carbonates resonance hybrid. Okay, so I'm going to draw that, right? First thing is you have to consider all the stable resonance structures. First point of drawing resonance hybrid is consider all the stable resonance structures, right? So drawing resonance hybrid, drawing a resonance hybrid. First concern is draw all the resonance structures, all the stable resonance structures, sorry for that, this is very important, no? All the stable resonance structures. Only stable guys we are concerning here. Draw all the stable resonance structures, right? That is the first concern, right? I'll write it in here. Drawing resonance hybrid, right? This is the first consideration. Draw all the stable resonance structures. That is first thing. The second thing, then from those stable resonance structures, first draw the common things. Draw the common things. Common things. Draw the common things appearing in the structures. Draw the common things. Let's draw the common stuff. What are the common things? Right? The skeleton is common. The atomic skeleton is common. Right? For all of these three stable structures, the atomic skeleton, that means atomic connectivity, it is common. Right? Common stuff. What are the other things which are common to all of these structures? When concerning this left hand oxygen, with the structure A, you have 2 lone pairs. With the structure B, you have 3 lone pairs. With the structure C, you have 3 lone pairs. So 2 lone pairs are always common for all the 3 structures. 2 lone pairs on this oxygen is common for all the 3 structures. So 2 lone pairs, it's a common thing. Draw all the common stuff, right? Common lone pairs, common bonds, common charges if available. You have to draw those common stuff for all the stable structures. With this oxygen as well, you have 3 lone pairs here, 2 lone pairs here, 3 lone pairs here. That means 2 lone pairs are always common to right hand oxygen. For the bottom oxygen as well, 2 lone pairs are always common with all the 3 structures. Draw the common things. Second thing, draw the common things. Third point, draw the varying components with the use of partial values. With the use of partial, that means half values. Let's do that. So your structure is written up to here. The common stuff have been written now. Now we are trying to draw the varying components, varying things. So what are the varying stuff here? The varying charges, varying bonds should be mentioned. First, let's come up with the varying bonds. Right. So you have this phi bond. You have this phi bond. At one structure it is appearing here. At the next structure it is appearing here. At the third structure it is appearing here. At the structure A here, structure B here, structure C here. So one phi bond is delocalizing on 3 places. One phi bond here, or here, or here. One phi bond delocalizing in 3 places. So one place get 1/3 of a phi bond. One phi bond in 3 places. One phi bond in 3 places. So one place get 5/3 of a portion. One place get 5/3 portion. 5/3. One phi bond delocalizing on 3 places. Lamai, always between 2 atoms the first bond is sigma. First bond is sigma. The bonds with the skeleton is sigma, are sigmas. The second bond and third bonds are considered as phi bonds. That is why I said this is a phi bond. That phi bond at the structure A appears here, structure B here, structure C here. That phi bond is delocalized in 3 places. So one place get 5/3 of a portion. Right? That is about the varying bonds. Varying charges then. So with the structure A, you have -1 on these 2 atoms. -2 charge on these 2 atoms. -1 each. At the structure B, -1 each with these 2 atoms. And the structure C, minus 1 on these two atoms. Actually, -2 charge, the -2 charge is delocalizing on 3 oxygen atoms. At the first structure, it is on these 2 atoms. At the second structure, first structure is on these 2 atoms. At the second structure, it is on these 2 atoms. At the third structure, the -2 is delocalizing on these 2 atoms. Actually, the -2 charge is delocalizing on these 3 oxygens when concerning the stable resonance structures. So, -2 charge delocalizing in 3 places, 3 oxygen atoms. -2 delocalizing in 3 places. So, one place, the one oxygen atom gets -2 over 3 kind of a portion. -2 over 3 kind of a portion for one oxygen. So, this is your resonance hybrid. This is your resonance hybrid. This is your resonance hybrid. Right now? So, that is how we are supposed to draw a resonance hybrid. Okay, so that is your resonance hybrid. Got the idea now? So, charges are clear, -2O2, 2O3 and the 5O3 here, resonance hybrid. Right? Let's draw few more. Before drawing the next structure, we'll discuss a bit more about the resonance hybrid. So, charges are clear, that is okay, and the partial bonds are there. So, actually there is a concept called bond order. There is a concept called bond order associated with the resonance hybrids, right? Bond order. So, what is this means? Bond order. Bond order means the number of bonds between considering 2 atoms. Bond order means that BO, bond order BO. BO means number of bonds appearing between considering 2 atoms. Bond order, right? Okay, let's consider the bond order of this structure. Bond order of carbon oxygen bond order. Here the carbon oxygen bond order, between the carbon and oxygen atoms, how many bonds are appearing? Complete sigma bond is there, and 1/3 of a 5 bond is there. Complete bond and 1/3 of 5 bond. That means complete bond and 0.33 of a bond. 1/3 of a 5 bond. 1/3 of a 5 bond. Complete sigma bond and 1/3 of 5 bond. That means 1.33. 1.33. 1.33 is the bond order between the carbon and oxygen. It is in between 1 and 2. It is in between 1 and 2. That is what I earlier said. The number of bonds in your naturally existing carbonate ion is not 1, not 2, but 1.33 between the carbon and oxygen. The number of bonds between the carbon and oxygen in naturally existing carbonate ion is 1.33. It is a value between 1 and 2. All these 3 CO bonds are with 1.33 as the bond order. Number of bonds between the carbon and oxygen is 1.33 here as well as here. Not 1 or not 2. It's the hybrid of all the 3 stable structures. Right now? That is the idea. This is how we are supposed to draw the resonance hybrid. Okay? So, these are the normal method. This is the normal method. This is the normal method of constructing a resonance hybrid. First coming up with all the resonance structures, then drawing the common stuff with those common bonds, lone pairs and charges, common things. Then we will draw the varying facts with partial nature, right. So ultimately we are able to come up with the bond order. That is very important in early calculations further, right, further calculations, right. So that is how we normally draw a resonance hybrid, right. Okay, so this is a symmetric molecule. For lamai, when it comes to symmetric molecules, I'll teach you a simple method. I'll teach you a simple method to come up with the resonance hybrid quickly without drawing all the stable structures. Without drawing all the stable structures, I'll give you a easy method, simple method to draw the hybrid easily. But anyway, you should know the right theoretical method, right, what was proposed by the resource book, huh? Okay. But to come up with a quick answer, right, I'll teach you a quick method. Okay, by leaving this thing like this, I'll come up with the more easy method, right, to do this one. Okay, right. I'll first of all I'll erase this thing. So if you have anything to write, so you can write those stuff, or you can have a screen capture as well. You can watch the video again, no? Right. I'll go with the next point, right. So it's like this. So let's quickly draw the resonance hybrid of the carbonate. Right, resonance hybrid of the carbonate. Right. I'll teach you another method. So actually this method can be applied only for symmetric skeletons, huh? Only for these kind of carbonate kind of symmetric skeletons, right? Not for all. Don't try to go for this thing with the asymmetric skeletons, right? Right. So for symmetric skeletons, see. First of all, draw a one stable structure. Draw, this is for symmetric skeleton, right? Then examples ගත්තම ඔය carbonate වගේ දේවල් ඔය phosphate වගේ කොට පුළුවන් ඉතින්. You can use this thing with these things, right? Phosphate, sulfate, SO3 2 minus, right? Few more things are nitrates. So you go symmetric skeletons, nitrates. So we have more, right? First, draw a single stable Lewis structure. Draw a single stable Lewis structure. So for the carbonate, so one single stable Lewis structure you can draw like this, no? So with the normal rules, you can draw one single stable Lewis structure, right? This will be the stable Lewis structure for one stable Lewis structure for carbonate. Actually, this is enough. This is enough to come up with the hybrid. This is enough to come up with the hybrid. See. One stable Lewis structure. And that is enough to come up with the resonance hybrid. Right, let's see what to do. Right. It's like this. Right. So actually, first of all, just see the symmetry of this thing. Just see the symmetry of this one. Symmetry. What is symmetry? Means lamai. So you have a double bond here. So first absorb the symmetry of this stable Lewis structure when you have a symmetric skeletons. When you have a symmetric skeletons, just absorb the symmetry first of all before trying to draw the resonance hybrid. Absorb the symmetry here. What is the symmetry here? See. So the symmetry is basically if you are with three lone pairs, those oxygens carry -1. 3 lone pairs -1. 3 lone pairs -1. 2 lone pairs no charge. That is there. That is one symmetry. You see. Then the atom with the double bond, the oxygen atom with the double bond carrying no charge, while the oxygen atoms with single bonds carrying -1 charge. Oxygen atoms with single bonds carrying -1 charge. Oxygen atom with double bond carrying 0 charge. That is the major symmetry with the bonds as well as the charges. Right. Let's use that symmetry to come up with the hybrid. So basically, with this symmetry, you could think of 3 resonance structures. Anyway, you could think of this double bond going to here and going to here. With this symmetry, you can think of this double bond coming to this place. If this double bond coming to this place, this oxygen won't get a charge, while this oxygen gets a minus charge. If this double bond happens to come to here, then it will be look like this, no here. Then this charge will disappear. This get a charge. Like that, no? Double bonded guys are without a charge. So that the only 2 lone pairs are appearing. Single bonded guys are with a charge. -1 charge with 3 lone pairs. When the double bond jumps to here, lone pair will disappear from this, and one lone pair comes to here and gets a minus here, and this minus disappears. The oxygen with the double bond won't carry a charge, while oxygens with single bonds carry -1 charge. That is how the structures become, right? Those are the stable structures. No need of drawing all the stuff first of all, right? So just by heart you can do so. Right, see, now let's draw the hybrid. So first draw the common stuff. When you see this, you feel that skeleton is always common. Skeleton means the atomic connectivity. Atomic connectivity is always common. First draw the common stuff with all the structures. 3 structures are there, right? Then with all the 3 structures, 2 lone pairs are common. When it comes to lone pairs, just think of the least appearance. The least appearance. Least number of lone pairs are the 2 lone pairs. Least appearance. So least appearance is always common. Now the varying stuff. So these 2 minus charges will delocalize among these 3 atoms. The 2 minus charges will delocalize. So on one atom, it is -2/3. 2 minus charge on 3 atoms, delocalizing on 3 atoms. So one atom gets -2/3 a portion. -2/3 portion. -2 charge, delocalizing on 3 atoms. Then the 5 bonds, varying 5 bonds. Only one 5 bond will be there at one structure it will be here, at the other structure it will be here, at the other structure it will be there. So one 5 bond delocalizing on 3 places, one 5 bond on 3 places. So one place gets 5/3 of a portion by one 5 bond in 3 places. So this is your resonance hybrid. This is your resonance hybrid. So you can comment on the bond order as well by looking at this. So bond order, the bond order here is one complete bond and 1/3 of a bond, that is 1.33. Right now? So that is the bond order. Right? So that is how we are supposed to draw the hybrid. So I'll do few more. Few more resonance hybrids to get the complete idea. Right? I'll do for the postpaid. I'll do for these guys as well. I'll do for postpaid PO for 3 minus, and then I'll do for sulfate, and I'll do for nitrate as well. Right? Okay. So you have some more stuff to draw, right, in your exercise book, right, in your Qt, right. Some more things are to be drawn, so you can do this as homework. I'll draw for these things, right. Okay. See, I'm coming up with the quicker method, right, the last method, right. So first I am drawing the Lewis structure, right. So this is PO for 3 minus. First I am coming up with one stable Lewis structure, right. Phosphorus carrying 5 electrons, 4 oxygens, one given 6 each, 3 minus, so 3 electrons should be added, more 3 electrons are there, that is 24 and 32 electrons. So electron pairs 32/2, 16 pairs, so right now 16 pairs. For the skeleton, this is your skeleton, 4 is used, 4 pairs are used, so remaining electron pairs are 12 pairs. So we can allocate them to the cone atoms to fulfill the octets, 4 pair situation. Then our next task is to minimizing charge on central atom, because the central atom belongs to third row or above. Central atom means the third row or above. So minimizing the charge on central atom, right. So before that we have to allocate the charges. So oxygens are with 7 electrons, 6 should be there for a neutral atom, but you have an excess electron, so -1 charge appears with these. Phosphorus should have 5 electrons as group 15, but you have allocated only 1, 2, 3, 4, 5 should be there, only 4 is there. So 1 electron, lacking of 1 electron, that means +1 charge is here. So you can neutralize these two guys by allocating a electron pair to here, right, giving electron pair to there, right, so that this charge will disappear with this charge while forming the bond here. right now. This is phosphate. This is phosphate. That is phosphate, right? Okay. So let's come up with the hybrid. Let's come up with the hybrid. So this is a symmetric structure. So anyway, for when drawing the hybrid, you can come up with the skeleton without a change, right? Skeleton won't going to be changed with the resonance structures, with all the stable structures, right? Okay. So what you see is, first write the common stuff, right? So you have an oxygen here, where only two pairs are appearing, lone pairs. But with these guys, three pairs are appearing. But when the double bond comes here, this oxygen will have only two electron pairs. When the double bond comes here, this will have only two electron pairs. When the double bond comes here, this will have only two electron pairs. The double bond oxygens are with only two electron pairs. So for all the four atoms, the common number of electron pairs are going to be two electron pairs. When the double bond delocalizes, right, the number of electron pairs will be limited to 2, right? This is the common stuff. Then we need to mark the varying stuff. First, the charge. So you have -3 charge at this structure bearing on these three atoms. When the double bond comes here, the -3 charge should vary on these three atoms, because double bonded atom is not coming up with a charge. The other atoms will come up with a charge. So when the double bond comes here, that -3 charge will delocalize on these three atoms. When the double bond comes here, that -3 charge will delocalize on these three atoms. When the double bond comes here, the -3 will delocalize on these three atoms. That means the -3 charge is going around all the four atoms, all the four oxygen atoms. That means one oxygen atom gets -3 over 4 of a portion. -3 going around 4 atoms. So one atom gets -3 over 4 of a portion. Such a portion is gained by one atom. Right? Right. Then the varying bonds. So here, this bond could be here, or here. 1,5 bond varying on 4 places. 1,5 bond varying on 4 places. So one place gets 5 over 4. 5 over 4 kind of a portion. 1,5 bond varying on 4 places. So this is your resonance hybrid. So normally resonance hybrids are, right, written inside brackets, right? So the bond order, if you don't need the bond order between the P and O in phosphate ion is equal to 1.25. 1.25. One complete sigma bond is there and 1/4 of a 5 bond. One complete bond and 1/4, 0.25 of a bond. 1.25 is the bond order for phosphate. Right? Ne? That is how we are supposed to come up with the phosphate. Right. The hybrid. Let's do few more with the sulfate. Okay, let's do with the sulfate. Right. After the phosphate, we are moving towards sulfate, the resonance hybrid. Sulfate. Right. Let's copy sulfate. Right? What it looks like. First the electron count. The 4 of oxygens. So 6 into 4, as group of oxygen is group 14. 2 excess of electrons. So this is 32. So electron pairs. 32 over 2, 16 pairs. So then we can think of the skeleton. For the skeleton, 4 pairs have been used. 4 pairs have been used. So the total number of pairs are going to be 12 pairs remaining. So those should be allocated to the skeleton. So to fulfill the octets of the covalent atoms, we have to give 3 more pairs each for all the atoms to complete the octets. So 4 pair situation, 1, 2, 3, 4. 1 is there, so another 3 pairs should be allocated. After this, we need to minimize the charge on central atom because it's a third row or higher situation, right? Third row element, right? So for that, first we need to come up with the charges. Before minimizing charges, you have to put the charges, right? So sulfur is group 16. 6 electrons should be there, but you have now allocated only 1, 2, 3, 4. 6 should be there, only 4 is there. That means lack of 2 electrons. That means plus 2 charge. Plus 2 charge. So you can minimize this charge by allocating a pair from here that will neutralize this charge. This will get a -1 and this will get a +1 from with that, and you can put it from another pair from here. So this one get a +1. The electron donor gets a +1. By electron acceptor get a -1. With this pair, electron acceptor, the sulfur towards sulfur, the electrons are given, gets a -1. Electron donor gets a +1. So that the charge will disappear. +1 -1 is 0. That will disappear when the electrons comes here. Right? This -1 -2 will disappear with the +2. While the electrons, that pair is coming here, this charge will also disappear. That is sulfate. So we are going to use this stable structure to construct the hybrid. First draw the skeleton. That is easy, no? First draw the skeleton. Nothing hard there, no? Drawing the skeleton. It is common always. So what will happen? First draw the common lone pairs. So 2 lone pairs will be common to all the guys. It will be common when the pi bond is delocalizing. All the guys should come up with a stage with 2 lone pairs, right? So the least number is written always. Common stuff. Then number of 5 bonds. Actually 2 5 bonds. 2 5 bonds can be delocalized in 4 places. In one structure it will be on these 2 places. At another structure, that 2 5 bonds will be here and here. At another structure, the 2 5 bonds will be here and here. When the 2 minus charges are carried by these oxygens, the 2 5 bonds will be here and here. When the 2 minus charges are carried by these 2 oxygens, the 2 5 bonds are here and here. So 2 5 bonds are going to delocalize among 4 places. 1, 2, 3, 4. 1, 2, 3, 4. 4 places. 1, 2, 3, 4. On those 4 places, the 2 5 bonds will delocalize. So what is the 5 bond node? 5 bond nature here. 2 5 bonds in 4 places. 2 5 bonds in 4 places. So one place gets half of a portion, half of I bond. That is simplified, half of I bond. So half of I bond, 5 over 2, 5 over 2. 5 over 2 is the bond load. 5 bond load, sorry, 5 bond load. What about charge? -2 charge is to delocalize among 4 oxygen atoms. 4 oxygen atoms. So -2 on 4 oxygen atoms. So 1 oxygen atom gets -2 over 4 of a portion. So that is also simplified like this. So half a portion. So half minus half. So this is your resonance hybrid. There is your resonance hybrid, right? Okay. So when you see the hybrid, when you see this resonance hybrid, you can say the bond load, the oxygen sulfur bond load is actually complete bond and a half of I bond, half of a bond. So 1.5 complete bond and a 0.5 of a bond. That is the bond load, right? Okay. So draw for the NO3 minus as well now. Draw for the NO3 minus as well. We'll discuss, right? Quickly draw. Right. Okay, let's quickly draw for the NO3 minus, right? Before going for the next section, right? So NO3 minus. So NO3 minus is a good molecule, right? To come up with, right? For resonance hybrid. So NO3 minus. First draw one stable structure for that thing. A nitrogen providing 5 electrons because it's group 15. 3 oxygens mean one oxygen gives 6 electrons each. Such 3 are there. Plus minus charge means one excess of electron is there. So altogether you are with 18 and 24 electrons. Then electron pairs 24 over 2, 12 pairs, right now? For the skeleton, this is the NO3 minus, this is the skeleton of that thing. Take in the least atom as the central atom. This is skeleton, right? So for the skeleton, 3 pairs are used. So you are ending up with 9 pairs to locate on those atoms on the skeleton. Right. So 9 pairs. So first you have to fulfill the octets of the corner guys. So 1 pair is there, 4 pairs should be given, right? So this is how we are supposed to complete the octets of the cone atoms. So 9 pairs have been given, right? Okay. After this stage, after locating all the 9 pairs, we have to think of the central atom. So here the central atom is second row non-metal. So the octet should be fulfilled. That means 4 pairs should be around the nitrogen. So we have to give the 4th pair. So that 4th pair can be given by one of these oxygens. So if you have to put this pair to here, like this, the 4 pair situation is achieved, right? Or one can give that from here or here, right? Anyway, one oxygen should give one of the pairs towards the center. Then the 4 pair situation, the octet is achieved. So that is done. After achieving the octet, we can allocate the charges when you have a second row non-metal at the center. So if you allocate charges, let's put the charges. So oxygen should have 6 electrons. Now you have 1, 2, 3, 4, 5, 6. So no worries, no charge. 6 should be there and 6 are there. Nitrogen group 15 should have 5 electrons. Now you have only 1, 2, 3, 4. 5 should be there. Only 4 electrons are there. That means it's plus 1. This oxygen 1, 2, 3, 4, 5, 6, 7. 6 should be there. Now you have 7. That means it is minus 1. 6 should be there. Now you have 7. That means minus 1. Here also the same, the minus 1. Right? So this is one stable Lewis structure for NO3 minus. So you can use this thing to come up with the resonance hybrid. So when it comes to hybrid, definitely the skeleton should be there. Skeleton won't change with the resonance structures. The skeleton won't change. So those should be there, right? Okay. The common stuff, right? The skeleton, atomic skeleton, the atomic connectivity. Right. Then you have these 3 atoms. So one location the 5 bond is here, the other it is here. In the other case it should be here. When the 5 bond goes like this, that the number of lone pairs also change, right? So anyway, least number is written, that is better, right? Those are the common lone pairs. When the 5 bond goes here, this guy is with 2 lone pairs. When the 5 bond comes here, this guy is with 2 lone pairs. The common number of lone pairs on these high oxygen atoms is going to be 2 pairs. Then the charges, then we have another common stuff, that is this plus charge. See, with all the 3 resonance structures, this plus charge will appear, even though this 5 bond to mark it here, the 5 bond to be marked it here, still this nitrogen get that plus charge. Even this 5 bond to mark it here, still the nitrogen get that plus charge. Plus 1 is always appearing with the nitrogen, right? That is the common stuff with all the 3 resonance structures. That plus charge is common for nitrogen, right? Okay, right. So if you need to draw, you can draw, right? If you need to draw, just draw. If you are not sure, just draw that stuff and see. The plus charge is common, right? So I had drawn another structure. See, you'll see the plus is common. Right? When the 5 bond is delocalized, still plus won't change, right? You can draw the other structure as well, the same thing, right? So what about the charges, the various stuff? Yeah. So with one structure, you have the neutral atom here, two minus charges varying on these two. And in the next structure, if the neutral atom is this one with the double bond, then these two guys will get the minus 2 charge, and if when the double bond comes here, these two will get the minus 1 charge each, right? That means minus 2 charge will delocalize on these three places. So one place get minus 2 over 3, minus 2 over 3, minus 2 charge, the minus 2 charge delocalizing on these three atoms, right? Minus 3, minus 2 in 3 places, minus 2, minus 2 in 3 places, 3 places. There is the partial charge, and then the 5 bond order, 5 bond. So that 5 bond will be here, here, over here, 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 over here. So one 5 bond delocalizing on 3 places. So 5 over 3, one 5 bond in 3 places, 5 over 3, 5 over 3, right? So that is the resonance hybrid of NO3 minus. So bond order of N and O is actually 1.5, no, 1.33, sorry, 1.33. One complete bond and a 1/3 of a bond. 1/3 means 0.33. Right, that is how the resonance hybrid looks like for the NO3 minus. Right, no? Okay. Right, that is about the resonance hybrid. So you have a very good example in your tute, right? That was the resonance hybrid drawn for N2O. Just go to that and see. There's a very good example. Huh? The resonance hybrid drawn for N2O is there in your notebook, in your book, right? At the page number 11. Just go to that, right? Resonance hybrid for N2O. It's a very good structure, right? Very good exercise, right? Go to that, right? Okay. So let's consider some more stuff regarding resonance hybrids, right? Regarding resonance hybrid, let's consider a few more stuff, right? Let's come up with another one. So NO2Cl, NO2Cl. So some another exercise appearing at the book. NO2Cl. Just draw this stuff as well. It is not a symmetric one. It is not a symmetric molecule. So it's a good exercise. NO2Cl. Right? Let's do that one as well. NO2Cl. Good one, right? Let's do. NO2Cl. First do the electron count. Nitrogen 5, 2 oxygens, 6 into 2. Chlorine group 17 gives 7 electrons to the valence electron count. So all together it is going 12, 19, 24. The electron pairs (24/2) is 12 pairs. 12 pairs. So for the skeleton, the NO2Cl is this. Right, NO2Cl is right like this, no? NO2Cl. 1, 2, 3. 3 are gone. So 9 pairs. 9 pairs. Right. Okay. Let's assign the 9 pairs for the corners first. One fulfill the octets. 4 pair situations. 1, 2, 3, 4. Right. 4 pair situations. 9 pairs. Okay. Right. This is not a symmetric one, right? Naman? This is not a symmetric one. So if you are dealing with this kind of situations, not a symmetric one, no, that's not that symmetric, no. Not all the guys are same, no. Not all the 3 connected guys are same, no. Not like in no 3 like that, no. So Cl is there, so these two are not same, no. So with this kind of situation, I prefer you to draw all the possible structures. Draw all the possible structures without doing it by heart, right? By memory, just draw all the structures, possible structures, and select which are going to be the ones contributing to the hybrid. Right. Okay. So to complete the octet of this nitrogen, you can allocate the pair from here. Right, that will give you this structure. That will give you this structure. Right, that will give you this structure. Right. With this structure, the oxygen is carrying -1 and nitrogen is carrying +1. So 1, 2, 3, 4, only 4 electrons are going there on nitrogen, that is +1, right? Or else, to complete the octet of this nitrogen, you can give the pair from here. Then you will come up with this structure. So with that structure, this oxygen is a minus and this nitrogen is a positive. Right? Or you can come up with this pair to complete the octet of that nitrogen. So with that structure, the thing will look like this. Right? This nitrogen carries a positive charge, and this carbon as well, chlorine as well. Sorry, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 7 should be there. Only 6 are there. Plus charge. Right? So those are the only 3 possible resonance structures for the NO2Cl. For the NO2Cl. Right? But when you are to draw the hybrid, you can't use this. You can't use this. Why? At the beginning I have said only the stable structures are to be considered. Only the stable structures are to be considered. These are the only stable structures. Negative charge on oxygen, adjacently connected atoms carrying opposite charges. These are stable structures. But here, this have a reason to become unstable. Adjacently connected atoms are with same sign charges, unstable, unstable. So we are not going to consider this thing when drawing the resonance hybrid. When drawing the resonance hybrid, this should not be considered. This should not be considered. Adjacently connected atoms carrying similar sign charges, repulsions will occur and bond will break. Repulsions will occur and bond will break. Unstable. Unstable structures can't be considered when drawing the resonance hybrid. So you can't use this one. So only by considering these two, you are supposed to draw the resonance hybrid. Draw the resonance hybrid. Let's draw the hybrid in here. Resonance hybrid. So with these two guys, the common, always the skeleton is common. Skeleton is common. Then you can think of the other common stuff. The +1 charge on nitrogen is always common. +1 charge on nitrogen is always common. And chlorine is always common. No change with the chlorine. No change with the chlorine. No change with the chlorine. And with the oxygens, you can have the double bond here. At that instant, two pairs here and 3 pairs here. When the double bond is here, only 2 lone pairs here and 3 lone pairs here. That is the situation. So always the 2 oxygens carry 2 lone pairs as common with this structure as well as that structure, right? And those are the common stuff. And varying facts. The charge in one stable structure minus charge is here. In the other stable structure one charge is here. So -1 charge varying on 2 places. At the first structure, red color structure, -1 charge is here. At the blue color structure, -1 charge is here. So -1 charge varying on 2 atoms. Not here, right? Not here. Only in those 2 cases, right? Because unstable thing is not considered. So -1 in 2 places. So one place get -1/2. This is the charge. This is the charge available. Then the partial bond. That phi bond is here or here. At the red structure, the phi bond is here. At the right structure, the phi bond is here. The phi bond is delocalizing on these 2 places. Phi bond is delocalizing on these 2 places. So one phi bond in 2 places. One phi bond in 2 places. So one place gets half of phi bond. Half of phi bond, 5O2. So this is your resonance hybrid. This is your resonance hybrid. So when it comes to bond orders, bond order here, bond order of oxygen nitrogen is complete bond and a half phi bond, 1.5. 1.5. Bond order of this thing, N and Cl, bond order of N and Cl is just 1. Just 1. Right now? That is how we are supposed to draw the resonance hybrid of NO2Cl. NO2Cl. Just quickly complete the stuff, Lamai. Just you can have a screen capture as well. Right now, NO2Cl is a good one. So only the stable structures are concerned when drawing the hybrid, right? When drawing the hybrid, only the stable structures are concerned. Right? Only the stable structures are concerned. Right now? Okay. Right. Finally, we will discuss what is the usage of finding this bond order. That is the final stuff to discuss today. We have calculated the bond order with each and every hybrid, and let's discuss what is the usage of finding this bond order. Why we are supposed to come up with this bond order? What is the practical usage there? let's discuss about that thing. The practical usage of bond order, right? Finding the bond order. Okay, let's see. Actually, bond order means number of bonds, covalent bonds between two considering atoms. Number of bonds between two considering atoms. That is what meant by bond order. Right? What is the importance of finding this thing? It is this line. Right? The idea is this, no? See? Right? If you are with single bond, then the bond order is 1. Only 2 electrons are there. At the center. Right? This single bond. This bond order is 1 single bond. When the bond order is 2, that means you are with 4 electrons in between the two nuclei. Then what will happen naturally? So these two nuclei, will be greatly attracted by 4 electrons. Two nuclei will be greatly attracted by 4 electrons than the 2 electrons. Right? Than the 2 electrons, 4 electrons will be greater than the 2 nuclei. Actually, distance between the nuclei, two nuclei is referred to as the bond length. So the bond length here will be smaller than the bond length here, because these 4 electrons will greatly attract the 2 nuclei, right? That means distance between the nuclei gets smaller when you are with more electrons at the center, as those 4 electrons are attracting, more electrons are attracting greatly the nuclei. So bond length becomes small. When the bond order is increasing, bond length is high here, less here. Bond length, when the bond order is increasing, bond length decreases. Bond length means the distance between two nuclei. This is very important to comment on the bond length. So one can say, when bond order BO increases, bond length decreases. Distance between two nuclei decreases. That is one very important usage of bond order. You can comment, you can compare the bond lengths with the use of bond order. We'll do such a question, right? So next thing, so you see clearly the overlap here is greater. the two nuclei are bound strongly here with 4 electrons. When the bond order is high, when the bond order is 2, that means 4 electrons. Here the two nuclei are bound strongly. Overlap is strong. So the bond strength is high here. Bond strength is high when the bond order is high. Bond strength is high. Bond strength is high. When the bond order is high, bond strength is high. Right? So those are very important facts. So we can use this bond order to compare the bond lengths as well as bond strengths. That is the most important usage of this bond order. Right? So we'll quickly do kind of example for this kind of a question. Right? We'll do a quick example. Actually, at the space given in your note, at the page number 11, with the point 2, at that space, just write this thing. At the page number 11, it is said, knowing the resonance hybrid is important to get the correct value of the bond order. Knowing the resonance hybrid is important to get the correct value of the bond order for the real species existing. If you know the bond order, you can compare the relative energies and lengths of the bonds. If you know the bond order, you can compare the relative energies and length of the bonds. Bond strength or the bond energy both are same. Bond strength increases means bond energy increases. Okay. So you can compare them if you know the bond order. So such two questions are there in your note. Let's do one of those quickly. See. So the question number 1. With the question number 1, what was the question? They have asked you to arrange these guys, NO3 minus and the NO2 plus, according to the increasing order of NO bond length, NO bond length. There's a question like that, right? And another question was there, we'll discuss both. They have asked you to arrange these guys in the increasing order of bond energy. Those two questions asked, right? Let's see how to answer these two questions, these kind of questions, right? Using this knowledge. So to comment on the bond length or the bond energy, first we need to come up with the bond order, number of bonds between the two corresponding atoms. First come up with this one, right? Okay. NO2 minus, NO3 minus and NO2 plus. Let's draw the structures of them. So I'll draw the structures, right? This is question number 1. Answer question number 1. Answer the question number 1, right? If I draw the structures, the NO2 minus will look like this. I'll just draw the structure quickly. NO2 minus. This will be one of the resonance structures you can draw for the NO2 minus. First draw the structures for all the guys. NO3 minus. NO3 minus. NO3 minus. No? First draw the simple structures, the NO2 plus. Draw some stable structures. NO2 plus. Right? Those are three guys considering. But we know these are not the existing structures in nature. These are not the existing structures in nature. This is okay. This is okay. This is the only structure we can draw. This is the only stable structure we can draw for the NO2 plus. So we can concern the bond order of this thing, this structure. But these are not the existing structures in nature, because we can draw more than one stable Lewis structure for these two, NO2 minus and NO3 minus. We can draw more than one stable Lewis structure for these two. So that we need to come up with the resonance hybrid. For these kind of questions, we have to always consider the existing structure in nature. So we have to consider this resonance hybrid for these. Let's draw the hybrids. Let's draw the hybrids. Let's draw the hybrids. With the hybrids, you can draw the hybrids for these two. So the hybrids looks like this. The hybrids look like this. For NO2 minus, minus half, minus half. You can draw these hybrids, right? We have just learned to. So 1 5 bond delocalized in two places. So 5 over 2 in one place. So the bond order of NO here is, bond order of NO is 1.5. 1.5. Let's draw the hybrid for this one as well. If you draw the hybrid for that thing, it will look like this. Right? Minus 2 charges will delocalize in 3 places. And here 1 5 bond delocalized in 3 places. So one place get 5O3. So the bond order is one complete bond and 1/3 of a bond, 1.33. 1.33. 1.33, right? So for this one, the bond order is very simple. Directly can be calculated. Bond order is 2. Bond order is 2. So now you have to compare these guys. What we are referring is actually about the bond length. Bond length. When the bond order decreases, bond length increases. Bond length and the bond order are with inverse relationship. So we can say like this. I'll write it here. Bond order variation is like the small bond order, right? Bond order variation will be like the smallest, the greatest is with this one, right? NO2 is the greatest, 2 no, then this one NO2 minus, then smallest with the NO3 minus. So bond length the other way around. So NO3 minus NO2 plus, right? NO2 plus is with the smallest length. Greatest bond order means smallest length. The sign changes. Minus and NO3 minus. Right now? So that is going to be the answer. That is going to be the answer. Right? So NO2 plus, NO2 minus and NO3 minus. Right now? So that is how we are supposed to come up with the answer. Right now? Complete. So do the working and come up with the answer. Right? So if you have more than one stable Lewis structure, so you can't consider it as the naturally existing structure. So for these kind of questions, naturally existing structure should be considered, so that we have to come up with a resonance hybrid. There, the bond order is there, and we have to go through the bond order to come up with the correct answer for the bond length as well as bond strengths. Right now? Okay. We'll do the last one as well. Right? We'll do the calculation for the last one as well for these 4 guys, right? Right. CO2, CO, carbonate and HCO2. Right? Okay. I'll erase this stuff. Right? So our second concern is about this, no? Right? Let's do the stuff, right? So CO2. So structure is this. So you have to come up with the structures. This is the only stable structure you can draw. The only stable structure you can draw. Other structures are actually unstable, right? So we are considering only stable structures, right? So this is the naturally existing structure. Its bond order is equal to 2 between the carbon and oxygen. Then carbon monoxide is there. The only stable structure you can draw, the only structure you can draw actually fulfilling the octet is this thing. Only structure you can draw fulfilling the octet is this thing, right? For the carbon monoxide. So its bond order is 3 between the 2 carbons, carbon and oxygen, sorry. Carbonate. So if you are to draw this structure for carbonate, it looks like this, right? But this is not the only stable structure you can draw for the carbonate, so you have to come up with the hybrid. So you need to come up with the hybrid. So naturally existing structure. So your hybrid will be like this. It comes hybrid, right? Only the common stuff are marked first of all. Then the partial charges. So -2 charge going on 3 places. In the partial 5 bonds. 1 5 bond on going around 3 places. So one place gets 5/3, 5/3, 5/3. So the bond order is 1.33. 1.33. One complete bond and a 1/3 of a bond. The HCO2 minus. HCO2 minus. The HCO2 minus, right? It's kind of this. HCO2 minus sorry, Hc2 minus, you can come up with like this, no, structure. This H2O2, HCO2 minus. So again you need to consider the resonance hybrid, because this is also this 5 bond can be here as well, right? Two stable structures can be written. So the hybrid, right, looks like this. So -1 charge on two places, and about the 5 bond, 1 5 bond in two places. So 5/2, 5/2, 1 5 bond in two places, 1 5 bond in two places, right now. So the bond order is 1 complete bond and a half a bond, 1.5. So when the bond order increases, bond energy also increases. When bond order increases, bond energy also increases. So greatest bond order is with this one, and smallest bond order is with this one. So the maximum bond strength or the bond energy is with carbon monoxide, maximum value, and the least value is with carbonate. When marking the other two, CO2 and HCO2 minus, CO2 is with the greater bond order, means greater bond strength or greater bond energy. Then the other one is here. So that is how you are supposed to come up with such an answer. That is the practical usage, right, of bond order. Right now, okay, right. So that is all for today, Lamai. So we have discussed about the resonance structures today to start up with. Then we had discussed about the resonance, the stability of the resonance structures, how to comment on the stability of those structures. Then we came to the resonance hybrid, and then the bond order and usage of that thing. The usage of the resonance hybrid have been discussed with some questions as well. Okay, then that's all for today, right? So with this, let's wind up at this stage, right? So next day we are going to discuss about a very important part, and next day we are going to discuss about drawing complex Lewis structures. So up to date we have discussed only Lewis structures with 1 or 2 central atoms, only 1 or 2 central atoms. But next day we will come up with Lewis structures with more than 2 central atoms, and for that we are not going to use this technique, we are not going to use this electron count technique for that thing. We are coming up with a different method. To quickly draw such complex structures. Actually, we can draw such a complex structure with more than 2 central atoms in no time, basically in 10 seconds. Basically in 10 seconds we can complete the whole complex Lewis structure when the structures are with more than 2 central atoms. We are using a different kind of technique, not the electron count technique, a different one. So with that we are able to do so even in 10 seconds. 10 seconds, right? We can complete the stuff. We'll discuss about that thing next day. Next day is all about that thing, right? So we'll wind up at this stage. Then goodbye then. Serious stick.